Welcome to Life with David. I'm David, and today I'm continuing my adventure into assembly programming of the RP2040. In my last two videos, we wrote, compiled, linked, and ran a simple assembly language program that blinked the LED on a Raspberry Pi Pico. However, there's only so much you can glean from a blinking light. As programs get more complicated, we need more sophisticated communications with the RP2040, either to convey information to and from the application or for debugging our programs. So why don't you join me as we explore three different methods of using the onboard UART to send and receive text between our assembly language programs and the outside world. Communicating between the Raspberry Pi Pico and the outside world is pretty easy when using MicroPython and Thonny. Using a print command with the appropriate formatting can yield fairly sophisticated output. Life is slightly more difficult when using C since a separate terminal is required. Usually a terminal emulator such as PuTTY and the USB port of the Pico are implemented. However, since USB communications are somewhat complicated, today we're going to use a UART or Universal Asynchronous Receiver Transmitter to communicate with the outside world using serial communications. This serial protocol is fairly straightforward. Each character is represented by a series of high and low signals. As you can see from this trace, the signal is high when the transmission is in the idle state. Transmission of the character begins with a drop to low level for 1 bit period, which is called, go figure, the start bit. 8 or 9 bits follow the start bit with the same period or baud rate until the character ends with a high-level signal, which is called, wait for it, the stop bit. A high-level signal represents a 1, a low-level signal a 0. The bits are transmitted with the least significant bit first. Sometimes a parity bit is added just before the stop bit for error checking, but that's pretty rare. Here, an ASCII capital U with its alternating bit pattern illustrates how a character is transmitted. This one is the ASCII lowercase p that illustrates the order of the transmitted bits. The RP2040 has two dedicated UARTs named, you guessed it, UART 0 and UART 1. UART 0 can use GPIO pads 0 and 1, or 12 and 13, or 16 and 17. UART 1 can use GPIO pads 4 and 5, or 8 and 9. Today we're going to be using UART 0 on GPIO pads 0 and 1. We'll use a UART to USB converter to connect a Pico to my Windows PC. You can get these on Amazon or eBay. I'll put a link in the description below for the one I used in this video. I connected the transmit lead from the converter to the receive of the Pico and the Pico transmit to the converter receive lead. There are several different terminal programs you can use on your computer to read and write to the Pico's UART. I'm using PuTTY. To find out what port your UART to USB converter uses, plug the USB connector of the converter into the computer while looking at Device Manager. Here I see that my converter uses port COM8. Then I configure the serial connection for 115,200 baud, 8 data bits, 1 stop bit, no parity, and no flow control. Note that while using your terminal program, the screen does not echo the keyboard. It only displays what is set to it from the Pico. To prove that the UART connection works, let's use a simple C program. Here we include the Pico standard I/O library. Inside the main program, we initialize the standard I/O and declare the character variable ch. Then we enter an infinite loop where we use getChar to grab a character that the UART received from the terminal and then use putChar to send the same character back to the UART, which then sends it back to the terminal. To select the UART, disable the USB and enable the UART in the CMakes list file. After we compile and link the program, I'll load it into the Pico. When I type a character on the keyboard, it's echoed on the screen. Since the UART works as expected, we can now move on to using it in an assembly program. For our first try in assembly, let's start easy. I'll create a C program that not only starts the assembly program, but also initializes the UART. Here we include the standard I/O library and define the function start. Then we initialize the standard I/O and then jump to the assembly program named start. In the assembly program, we start the program and then enter a loop where we call the C function getChar to read a character from the UART into register 0. Then we use the putChar function to write the character in register 0 to the UART and eventually to the terminal. Then we use a branch instruction to do it all again. Let's try it out. Just like the previous demonstration, when I type on the keyboard, the character is echoed to the screen, just as expected. It worked, but it was pretty simple. Remember, this is Adventures in Bare Metal Programming, and that was hardly bare metal. So let's dip our toe into the UART registers. Each UART on the RP2040 has a transmitter to send the data to the terminal and a 32-character FIFO to buffer the transmitter. It also has a receiver to receive data from the terminal with a 32-character FIFO to buffer the receiver, a bus interface to connect the UART to the processors, and other status, interrupt, and DMA interfaces. In this demo, we're only going to worry about the read and write data registers and the FIFO flags, which will tell us if the FIFOs are full or empty. I'll let the standard I/O UART init C function set up the rest of the UART for this demo. If you think that's cheating, don't worry, we'll get into the weeds shortly. We can refer to section 4.2.8 of the RP2040 datasheet for a description of the UART registers. UART DR is pretty straightforward. We read it to get received data from the FIFO and write to it to send data from the processor to the FIFO to be transmitted. However, we need to know when the data is available in the received FIFO or when the transmit FIFO is full so we can stop sending information. That's what the flag register UART-FR is for. We'll monitor bits 4 and 5 to see if there's data available or if the transmit FIFO is full. Let's look at the program for Demo 3. Because this is a more complicated program, I'll include the routines to turn the LED on and off to help with debugging. This is similar to the LED blink program in Chapter 1. After we set up the LED, we enter the communications loop. Here we first branch with link to the UART0in subroutine to read data from the terminal, and then branch with link to the UART0out subroutine to write the same character back to the terminal. Let's look at the UART input and output subroutines in more detail. We'll start with the input subroutine. First, I'll preserve the value of the registers 1 through 3 as well as the link register by pushing them onto the stack. This is a good habit to get into for every function or subroutine. Then we enter a loop where we first load in the base address for the UART0 registers into register 1. As you can see from section 4.2.8, that address is 40034000 hex, which we then assign to UART0RW in the data section. Now we want to check to see if the UART has received any data. We'll load the UART0 flag register, which is at an offset of 18 hex from UART0RW into register 2. To isolate the received FIFO empty flag, which is bit 4 in the flag register, we'll load 16 decimal into register 3. Then we'll AND registers 2 and 3. This will eliminate all the other bits except for bit 4. If bit 4 is set, then the received FIFO is empty and no new data has been received. If bit 4 is set, then we'll use a branch if not equal to jump back to the beginning of the loop so that we can check it again. If bit 4 is cleared, then the received FIFO has some data in it, and we can read it from the UART data register, which is at offset 0, into register 0. To return from this subroutine, pop registers 1, 2, and 3 off the stack, and then load the program counter with the value of the link register. When using the stack, this is the ARM preferred way of returning from a subroutine. When the link register is loaded into the program counter, execution of the program immediately continues with the next program location after the subroutine was called. The UART output subroutine is similar. It will transmit the data that is in register 0. First, we push the 4 registers onto the stack and then enter a loop where we load the base address of the UART registers and then load the UART flag register into register 2. This time we want to test to see if the transmit FIFO is full. If it's full, then it can't accept any more data, so we need to wait until there is space available. The transmit FIFO is full if bit 5 of the flag register is set. To isolate bit 5, we load 32 decimal into register 3 and then AND registers 2 and 3. If the result is not 0, then we jump back using a branch if not equal and then check again. However, if space is available, we prepare the data for transmission. We only want to transmit out 8 bits, so we first load a bit mask of FF hex into register 2 and then AND it with our data that is in register 0 and put the results in register 0. This isolates the 8 least significant bits of the 32-bit register. We'll store the character in register 0 to the UART 0 data register at offset 0 from UART 0 RW. Then we'll return from the subroutine by popping registers 1 through 3 off the stack and then loading the program counter with the value of the link register. The debug subroutines that follow are there to turn the LED on or off while developing the program. We don't use them during normal program execution. Finally, here's the data section of the program. Okay, let's compile, link, load, and run the program. Perfect. Again, we see the characters I typed are echoed on the screen. Now that we know that we can read and write to the UART registers, let's dive into some bare metal programming. Here we will initialize the UART without using the standard UART init C function. Again, the RP2040 datasheet is our guide. I'll refer to the Programmer's Model section 4.2.7 for details on how to initialize the UART. However, before I get into initializing the UART, I've added some debugging routines. Here I initialize the LED so I can turn it on or off. Next, I verify that the crystal oscillator is stable and then port it to GPIO pad 21 so I can verify its frequency with my scope. The first step in initializing UART is to reset it. I want to start with a clean slate, so I'll use the reset registers just as we did in Bare Metal Adventures Chapter 1. In section 2.14.3, we see that the UART 0 reset state is controlled by bit number 22. I'll use the atomic register, which is located at an offset of 2000 hex from the reset register, to set bit number 22 of the reset register to reset UART 0. Then I'll bring UART 0 out of reset. By using the atomic register at an offset of 3000 hex from the reset register, I'll clear bit number 22 of the reset register. It takes some time for the reset to complete, so I test the reset done register located at an offset of 8 from the reset base address by ANDing the results with a bit mask that isolates bit number 22. If bit number 22 is a 1, then the reset is complete. If not, we'll check the status again. When the reset is finished, I'll set the peripheral clock. The RP2040 has several different clocks that various systems and peripherals can use. The sources include the on-chip ring oscillator, the crystal oscillator, external clocks from the GPIOs, and the phase lock loops. Each clock source has its own advantages and disadvantages. We won't get into the gory details at this time. We'll just choose the 12 MHz crystal oscillator that's on board of the Pico to supply the clock for our UART, since it's very stable. As we can see from section 2.15.7, the registers to control the clock settings start at 40008000 hex, which we will assign to the variable CLK read-write and load into register 0. The peripheral clock has an offset of 48 hex from that base address. As you can see here, we need to set bits 11 and 7 to enable the crystal oscillator for the peripheral clock. First, load 1 into register 1 and then shift it left 11 places. Then I'll add 128 to set bit 7. Finally, store that value into the peripheral clock register. Now that the clock source is set for the UART, we need to enable the UART. We use the UART control register, which is located at an offset of 30 hex from the UART register base address of 40034000. We'll set bit 9 to enable the UART receiver, bit 8 to enable the UART transmitter, and bit 1 to enable the UART as a whole. We will load 3 into register 1, shift it left 8 bits, and then add 1 to create the required bit mask. Then we'll store that value in the UART CR register at offset 30 hex. Next, we need to set the baud rate for the UART. Remember in Demo 1 that we set the baud rate of the terminal to 115,200. That's the default value for the C UART initialization function. However, we're not going to be using that function at this time, so we have to set it ourselves. The UART speed is set by writing integer and fractional divisors into the UART IBRD and UART FBRD registers respectively. The values are calculated by dividing the peripheral clock frequency by 16 times the desired baud rate. Since the crystal oscillator is running at 12 MHz, the baud rate divisor will be 12 MHz divided by 16 times 115,200, or 6.51. The integer part of the divisor is 6, and the fractional part is 0.51 times 64 plus 0.5, which equals 33. Therefore, we load 6 into register 1 and store it in the UART integer baud rate divisor register, which is at an offset of 24 hex from the UART register base. Then we load 33 decimal into register 1 and store it in the UART fractional baud rate divisor register, which is at an offset of 28 hex from the UART register base. Now we need to set the word length and to enable the FIFO registers. We do this in the UART LCR-H register, which is located at an offset of 2C hex from the UART register base address. I'll set bits 5 and 6 to set the word length to 8 bits, and I'll set bit 4 to enable the FIFOs. We'll do that by loading decimal 112 into register 1 and then storing it in the UART LCR_H register. The last thing we have to do is to route the receive and transmit lines of the UART to the GPIO pads. From 1.4.3, we can see that we need to assign function 2 to GPIO pads 0 and 1. We do that by writing 2 decimal to the GPIO 0 CTLR and GPIO 1 CTLR registers, which are located at offsets of 4 and C hex respectively from the IOB register base. Next, we enter our communications test loop. The UART 0 in and UART 0 out subroutines are exactly the same as the previous demonstration. Since we have defined all the UART initialization functions manually, we can delete the UART initialization function from our main C program. The main program simply becomes a way to start the assembly program. Let's compile, link, and run this program. It looks like it works just like the other ones. Success! Thanks for joining me today. We explored 3 different methods you can use to communicate between an RP2040 assembly language program and a terminal. We learned just a little about clocks and were able to connect another device to the GPIO pads. I've discovered that debugging assembly programs is challenging, so next time I'll put together some simple routines to help in the process by using text output. I'm planning on digging deeper into low-level programming in the future, so stay tuned. If you like this video, or you think someone else might, please give it a thumbs up. If not, give it a thumbs down. The more likes this video has, the more YouTube will recommend it to others. Also, please leave a comment or suggestion for things to do. I hope to do more of these videos, so please subscribe and click on the bell for notifications of new videos. Let's get together next time for another day in Life with David. See you soon!